Now we've looked at increasing and decreasing portions of the curve. We've looked at when we have the derivative, it's either bigger than 0 or less than 0, and that tells us whether the function itself is increasing or whether the function itself is decreasing. There's one thing that's missed out there though. What happens if the derivative is equal to 0? Well, if the derivative is equal to 0, there is no increase or decrease, and that's where something special comes into play, and that's what we're going to look at in this video. What we're going to look at is stationary points of curves and looking at determining their nature. Now, the easy way to think of a stationary point is this. It's a point where the graph is no longer increasing or decreasing. For that tiny micro millisecond, that tiny space of the graph, it's flat. Now, I'm talking tiny, it's microscopic. Everywhere else it's increasing or decreasing in some way, shape or form, but this is the time when it's not. So your derivative is equal to 0. Now, there are 4 types of stationary point we are going to come across, and they look like these 4 scenarios here. So you've got a scenario that looks like this, one where it's coming up and back down, and curves that look like this. So you're talking this is maybe your cubic, and these would be maybe your x squared, so negative x squareds. And these all have a different type and a different name. This one here is what's called a minimum turning point. Now what it means by that is it's a point, you'll notice, where the graph turns back on itself, but it's also the minimum, i.e. the lowest point on the graph. So if you're ever asked to calculate a minimum turning point or a lowest value, that's what it's meaning. This one here, coincidentally, is called a maximum turning point. And it's for the same logic as the minimum one, the only difference being it's the highest value the curve will ever reach. So it goes up to this value and then comes back down and decreases on forever. So it's the maximum, i.e. the highest point where the curve goes. These two here, not so much, because the curve comes up, goes through it and keeps going, or comes down, goes through it and keeps going. These both have special names. These are what's called points of inflection. Alright, these are points of inflection. So these are points where the curve stops briefly but then continues on the journey it's going. So it stops briefly and then continues, or it stops briefly and continues. Now each of these have a different type though. They're both points of inflection, but this one here is what's called an increasing point of inflection. So if you look at the derivative either side of it and see the curve, it's increasing every other value through it except that point there, the point of inflection. And coincidentally, this one here is decreasing. So if you look at every value beyond the point of inflection there in the middle, it's coming down the way. It's always going down. So it's a decreasing point of inflection. So these are the 4 different types that we can work with. Now, determining how these occur, what they look like, and actually which one we have in a graph, it's actually fairly straightforward. It's just getting used to the technique. So the 4 steps you should always do whenever it comes to calculating a turning point and its type should be this. First thing you should always do is calculate the derivative. So find your f dashed of x or dy by dx, obviously depending on the format they give you the equation of the line in. Second thing, set it equal to 0. Remember, there's no change, there's no increase, there's no decrease at a stationary point, so your derivative is equal to 0. You then solve it and you find the x part of the coordinate. Now remember, there could be 1, 2, 3, 10, 12. You solve it and find them all. Third thing you then do is substitute the value you got for x here into your original function to find the y part of the coordinate. So then you've got your x and your y part of it, you know exactly where the coordinate is located. Last thing is you then use something called a table of signs to calculate the nature of the point. And I'm going to show you that in a second with the example. And this table of signs will show you how the graph behaves just before and just after the point. So it'll give you an idea what it looks like leading up to the stationary point and then what it looks like after it. So you can determine which of the 4 types it will be based on that. So here's an example for you. So I want to find the stationary points of f of x equals x cubed bracket x minus 4 and determine their nature. Now remember, the first thing we want to do is find the derivative. So to do that for this, I'll multiply out the bracket to start. I've got to have it term by term. So that gives me x to the power of 4 take away 4x cubed. Now I calculate the derivative, the f dashed of x. Calculate that, bring the power down, reduce by 1. I get 4x cubed, bring the power down again. I get 4 times 3x squared, which gives me 4x cubed. Take away 12x squared, And to get my stationary point, this is where the second part comes into play. That equals 0. And I have to solve it now and figure out the values of x, which that works for. So looking at this, factorise it, I could take out 4x squared as a common factor, and what I end up getting is x take away 3, and that equals 0. So here I get two possible solutions for it being equal to 0. Either this bit's equal to 0, or this bit here. So what I know is that 4x squared equals 0, so x is 0, or x minus 3 is 0, which means that x equals 3. So there's my two stationary points on the graph. That's where it's turning. So those are the two stationary points I need to find. What I now need to do is use my table of values after I calculate the y parts to get what kind they are. But do the y parts first. So if x is equal to 0, I substitute into here. I get 0 times something. Well, that's going to be 0. So that means y is equal to 0. So my first turning point is the origin, 0, 0. Second one is substituting in 3. So I do 3 cubed, well 3 cubed is 27, times it by 3 take away 4, which is negative 1. So I know for this one, y is negative 27. So my second turning point is 3, negative 27. So now that I've got the 2 points, I can do my nature tables. I can do these to figure out what kind of stationary points they are. So now look at the first one. And the way you set up a nature table is always the same. You've got 4 columns. This column here, so second from last, is always the value where your x part of your turning point is. So in this case it's 0, so that's where that goes. This one here, you imagine that's just below 0, so some value just below 0. And this one here, some value just above 0. You then have 3 columns as well. Your first column with your values, your second column with your derivatives. So in this case, I know my derivative is f dashed x, so I'll put that in. If your derivative is something different, so maybe dp by dt or dy by dx, depending on the scenario of the question, always put that in here. Don't always put f dashed of x. Put whatever your derivative is called in here. And then this last one is the graph. How does it look? What we need to do now that we've set up our table, is start to determine how it looks. So what we have to do is pick values and substitute them into our derivative, so this one up here, and see how that behaves. See whether it's telling you if it's increasing or decreasing and how the graph looks. Now your turning point, your stationary point, if you substitute that into the derivative, should always give you 0, because you know at that point it's going to be flat. There's no change, it's not increasing or decreasing. That's what it's going to look like. What we want to do is then look at a value just below it and then just above it and see how it behaves either side of it. What does it look like? So let's imagine just below it we pick a value like negative 1. Let's pick something like that. So imagine I've got negative 1 here and I substitute it into this. So I'd get negative 1 cubed, so that's 4 times negative 1, which is negative 4. I'd get negative 1 squared, which is 1, so that's 12 times 1, which is 12. I'd then have negative 4, take away 12, I'd have negative 16. So I know my graph is going to be negative at this point. So it's going to be coming down. Think what a decreasing graph looks like. It's coming down the way. Imagine I then pick a value just above it, so let's say 1. I'd end up with 4 times 1 cubed, which is 1, so I'd get 4. Take away 12 times 1 squared, which is 1, so it's going to be minus 12. So 4 take away 12 gives me negative. So I know it's going to be negative above it too. So what that means is the graph above it is going to come down like that as well. So this means that my graph is going to look something like coming down there flat and coming down. Well, we know that's a decreasing point of inflection. So we know what kind of stationary point it is. It's a decreasing point of inflection. It's going to look like that at the origin. So 0, 0. Perfect. Now we can do the other point, the 3, 27. Negative 27, sorry. And we can set it up the exact same way. So same table, like this. F dashed of x in there. Again, make sure the name of it's correct. Graph in the bottom. And we know the point that we're looking at in terms of x is 3. So 3 goes in the middle there. And I want a value just below 3 and just above 3. Now, one thing I'm going to tell you to make sure you take into account, 2 x values here are 0 and 3. Now, they're not next to each other, but they're still close. Do not pick them as the values above or below if you can. So I've got 3 here. The value I pick below, I could pick anything between 3 and 0, but I can't pick 0. And then the 3 above, well, I've no other values above it, so I could pick anything. But say I ended up with a 0 and a 1. The value above 0, you don't pick 1. The value below 0, you don't pick 0. You go in the middle, you maybe take a half. Be very careful of that. So, x is 3, substitute into the derivative, you get 0. So I know at that point it's going to be a flat graph. Look just below 3, so let's imagine we take 2. I get 4 times 2 cubed, so 2 cubed is 8. 4 eighths are 32. 2 squared is 4. 12 fours are 48. That's going to be a negative value. So it's going to be coming down that way. Imagine I go above it now. So let's say we go just above 3. So I've got 4 times 4 cubed, take away 12 times 4 squared. 4 times 4 cubed gives you 256. 12 times 4 squared is 16. So 12 16s gives you 192. 256 take away 192 gives you something above 0. So for that one, I get a positive value. So the curve's coming up. It's increasing. So at this point, the graph looks something like that. What that means I've got a minimum turning point at that one. So I've then determined the nature of my 2 points there, my 2 stationary points. I know the point 0, 0. What that is that's a decreasing point of inflection, so a decreasing POI. And the other point, 3, negative 27, I know that is a minimum turning point. So I've determined the nature of both of those. Now, it's a longer process, and it seems when you get in the habit of it and you get in the routine, it's actually quite straightforward, and it's always the same way. Take your derivative, equal to 0, solve it for x, find your y part, you've got the full coordinate then use your nature tables. It's a fairly straightforward process once you get into the swing of it and once you get into the habit.